Okay, welcome to the IMA Northwest Branch Maths Education Talk, Python for A-level mathematics and beyond. Stephen Lynch, who's giving the talk, is the Deputy Head of Computing the Computing and Mathematics Department at Manchester Metropolitan University. He has over 30 years experience in using programming in his teaching and research, and he's also written numerous books on Python, Maple, MATLAB and Mathematica. So he's very well placed to make us think about the introduction of programming to mathematics teachers. If you have any questions, please put them in the Q&A section rather than the chat, and we'll save all of the questions for the end of Stephen's talk. Today's talk will be recorded and put on the IMA's website. So without further ado, I'd like to hand over to Stephen for today's talk.
Okay. Thank you, Rachel, and thank you, Keris, for organising this. So I'm going to talk about Python for A-level mathematics and beyond. As you can see, I'm a fellow of the IMA and I'm also a senior fellow of the Higher Education Academy. And the picture here was generated with Python, and at the end of the talk, I'll show you the program to generate this image. So the aims and objectives, I want to show you how Python can enrich the teaching and learning of A-level mathematics. I'm also going to show how Python can help you to solve real-world problems. Now, a lot of my research, well, nearly all of my research, I need these maths packages to get my results. And then hopefully I'm going to reveal that maths with programming is a much loved subject by our students. And hopefully at the end of this presentation, you'll be inspired to incorporate Python or MATLAB or Maple or Mathematica into your own teaching and learning. But I think for A-level, it will probably be Python. Okay, so there are, as you know, 4 majorly used packages in mathematics. They are MATLAB, Python, Maple, and Mathematica. And as you can see, I've written books on all of these topics. If you go to my web page, so the URL is at the top, or you just type in Stephen Lynch, Manchester Metropolitan University. You can get to my personal website. If you click on the Springer links, then this gives you information about the books and it breaks down the chapters for you. There are also links where you can download the programs or look at the web pages, etc. And then below this, it shows you the number of chapter downloads according to Springer. And since about 2010, my books have had nearly 500,000 chapter downloads. So these books are very popular. And as you can see in the title, these packages are used to solve real world problems. And I use them extensively in my own research. Okay, so if we're talking about programming languages, I think I've been reading about this, and I think there are estimated to be about 600 live programming languages at the moment. If you look on Google, I found some stats from Statista and from this DevSaran, and looking at the most popular programming languages in the world at the moment. And I'm sure you'll not be surprised to see that Python, Java, JavaScript, C#, etc. are always at the top of these lists. This figure here shows that 31.2% of the world uses Python, about 20% use Java, etc. So then the obvious question then, as mathematicians, is which language should we be using, if at all, to teach programming to students? Now, at Manchester Metropolitan University, for the past 20 years, we have been using MATLAB. So we use MATLAB. But you can see, even according to Statista, there are only about 2% of users around the world. So when we think about employability, is MATLAB the best programming language to teach our students? Okay, and then we think of these other languages. Which language is appropriate for mathematics? And again, I've had a look at a lot of these languages, and Python is definitely suitable for mathematics, and hopefully you'll see why as I go through this talk. Languages such as Java, I would say, are not suitable at all for mathematics. If you want to write a simple program in Java, for mathematics, it can be quite a few lines, whereas in Python, it could be just 1 or 2 lines. So some of these other languages are not really suitable to teach mathematics, but Python is not only ideally suited to teach mathematics, but as you can see, it is used extensively around the world, and it is a general purpose programming language. So I'll give you a bit of history now. So I did my PhD at University College Wales, Aberystwyth from 1985 to 1988. And my problem I was working on was the second part of Hilbert's 16th problem. So we were trying to find a bound on the number of limit cycles for planar polynomial systems of the form dx dt is a function of x and y, and dy dt is a function of x and y. Now, I'm not sure how many of you have heard of the second part of Hilbert's 16th problem. It's quite famous within mathematics. It's quite a simple problem to state, but it is proving to be remarkably intractable. Okay, we haven't even got solutions for simple planar systems, and these have to be non-linear. So here we have a picture of David Hilbert, and if any of you watch Netflix, there was a show called The Umbrella Academy, and they were traveling through time, etc. And you'll see here that in order to travel through time, they actually needed to prove the existence of a bound on the number of limit cycles. So in the show, they claim to have proved found a solution to Hilbert's 16th problem. Okay, so it's great to show our students this, see it in the news. Okay, so I'm now going to talk about limit cycles. Okay, so these are ideas from pure mathematics. And as I say, I did this for my PhD, or I should say, while I was studying for my PhD, in the mornings, I would read very pure mathematics papers. And I'm sure if any of you have read pure maths papers, they can get quite boring. And in the afternoon, I would go on the computers and do symbolic computation and computer algebra. And I think this enabled me to complete my PhD early because of the variety. So not only was I doing the pure mathematics, but in the afternoon, I was using these computer packages to help solve the problem. And I think that variety helped me cope with the studies. And I actually completed my PhD studies in 2.5 years. So I completed them early. So a limit cycle is an isolated periodic solution. Here we have an example with 3 limit cycles, and this is from a Morris-Lacar model of a motor neuron. So Morris-Lacar, we're looking at motor neurons in giant barnacles. And here we have, so these limit cycles represent oscillatory behavior. And barnacles are not the only species which are full of these oscillatory behaviors. So we think of our own human bodies. In our brains, we have neurons. So we have cells called neurons, and they oscillate. So the cells in our brain oscillate at about 1,000 times per second. But they are not the only oscillators in the body. Retinal cells in our eyes oscillate. Muscle cells oscillate. And then so our bodies are just full of these oscillators, and they all oscillate on different time scales. Okay, so here we have, and I'm going to show you an animation now, which was produced in Python. So the phase portrait on the left was produced in Python. So we have 3 limit cycles. The green in the limit cycle is a stable limit cycle. The red one is an unstable limit cycle, and the blue one is a stable limit cycle. So let's suppose we give some stimulus to this neuron. So we'll just run this video, and we start with a critical point here. So we just have a stable point, and you'll see that a small oscillation grows. So we have this small amplitude limit cycle grows, and as the stimulus grows into this neuron, you see we jump from one limit cycle to another limit cycle. And this is called a hard or a dangerous bifurcation. Okay, why is it called hard or dangerous bifurcation? Well, if we now have a look at an example from engineering, so the video on the left is going to show an aircraft about to take off, and the video on the right, I know I've just shown you this for the neurons, but we have similar graphics for these characteristics of these engines. So if I just run these videos, so as the plane is about to take off, so the limit cycle is representing the nonlinear characteristics of the jet engine. So we're going along nice and smooth. I should say that this is all in slow motion. And we have a sudden jump to another limit cycle. And this is where we get our surge in the jet engine. And you see the engine stops working. Okay, so this is why it's called a hard or a dangerous bifurcation. So we've bifurcated from a small amplitude limit cycle to a limit cycle of larger amplitudes. And you can get these surges in jet engines. There are also other examples in engineering, again, to do with, for example, aircraft. So you can have these jumps and we get something called wing rock phenomena in aircraft. So your aircraft can actually tip because of this jump from one limit cycle to another limit cycle. So hopefully these animations are showing you that you can go from pure mathematics, where we're looking for limit cycles and number of limit cycles, to actual physical applications. And the example I showed you just before with the Morris-Lacar neuron was actually a piece of coursework for our final year students a few years back. So you can see we can give them actual physical models using Python or MATLAB. And this obviously helps with employability later on. Okay, so now let's talk a little about A-level mathematics. So I've got two simple animations here. The animation on the left is we're going to show how a tangent moves around a parabola as x varies. And you'll notice at the bottom, there are three options here. We can just show the animation once, we can loop the animation, or we can reflect the animation. So in the first case, on the left, we are just going to loop the animation. So this is how the tangent moves around the parabola as x goes from -4 to 4. And then we loop again. So here is the animation of the tangent as x goes from -4 to 4. So you can see the tangent goes from negative gradient, 0 gradient, to positive gradient. Okay, now again, when we're discussing problems in the real world, when we solve a lot of real world problems, we do end up with periodic solutions. And that's because we live in a periodic world. And our world exists within a periodic solar system. So everything is driven periodically. So it's no surprise really that our human bodies are full of this oscillatory behavior. So the animation on the right I'm going to show you now is, we're going to show a reflection. And this shows what happens as a parameter increases and decreases. And this is very useful when we're modeling systems in the real world. So if I run this second animation, you'll see we are increasing the frequency of oscillation of our sine wave. And then we decrease the frequency of the oscillations of the sine wave. And again, we increase the oscillations. And we could carry on like this forever. But if you think about it, in our periodic world, this is what is happening all the time. Our systems are being driven periodically. Okay, so for example, in the day, in the morning, we wake up and it's quite chilly. And then towards the afternoon, it gets warmer. And then it goes cooler again towards the evening. And then it all kicks off again. Okay, so we're on this constant cycle. So we have all these oscillations. So Python can help with teaching. It can help paint these pictures. So there's a famous saying, a picture can paint 1,000 words. Well, you can think of these animations as painting 1,000 pictures. So in effect, animations are painting 1,000,000 words. As I say, we've been using maths packages in our teaching at MMU now for over 20 years. In 2011, the Students' Union at MMU started a competition, and they've asked students to vote for their favourite lecturer, favourite course, etc. I think currently there are somewhere in the region of 38,000 students at Manchester Metropolitan University, and they're in the region of about 600, 700 different courses being offered at MMU. And you will notice here that in 2020, 2018, and 2012, mathematics was voted course of the year by our students. And you also notice we were shortlisted in 2011, this was the inaugural year, 2013, 2014 and 2019. So this competition has been running for 10 years and mathematics has been shortlisted on 7 occasions, and we've actually won the award 3 times. Okay, and we believe that one of the reasons that our course is so popular is because of the amount of programming we do with our students, which enables us to solve real world problems, and there are other aspects to this which I'll discuss during the talk. By now, I think probably most of you have heard of these government reports. So in 2018, the government published a report called the Blackett Review, and this was looking at computational modelling and technological futures, and it highlighted the importance of mathematical and computational modelling to the economy of the UK. Okay, I think we've all, as mathematicians, we've all known for a long time that mathematics is vitally important to the economy of the UK. So this report goes into detail about that. And then shortly afterwards, Philip Bond published a report, and this was an independent review of knowledge exchange in mathematics. There were a lot of recommendations, but as you can see, recommendation 8 was that all mathematics students should acquire a working knowledge of at least 1 programming language. So that was as a result of this report. Okay, I think you'll all be surprised by this next piece of information. So as I say, at MMU, we have 38,000 students. So in October, we've arranged some open days, where prospective students come and have a look, well, virtually around the university. And just lately, these numbers are typical of the numbers of students we're getting in for these courses. So you notice we've got 72 students coming in for biology, 73 students coming in for biomedical and physiological sciences. We have 18 students coming in for chemistry, 37 coming in for computer games and animation, 74 coming in for computing, 49 coming in for engineering, 76 for geography, and 16 students are coming in because they're interested in the mathematics course. Now, sport and exercise sciences within the Faculty of Science and Engineering, we've got 152 pupils coming in, and they're interested in doing a degree in sport and exercise science. And I'm not sure how many of you are aware that mathematics is the most popular A-level, and it has been now for a number of years. So at A-level, maths is the most popular subject, but you can see when it comes to university, mathematics is one of the least popular subjects at university level. Okay, so now I'm going to show you how you can download Python onto your computer. You need to go to a web page called www.anaconda.com, and from that web page you can download the Anaconda Navigator. So you download the Anaconda Navigator. You can do this through through Unix or through a PC or a MacBook, etc. And this is what the Anaconda Navigator looks like. So I'm going to give you a brief introduction to the Jupyter Notebooks, also Spyder. So these two are where we use Python. And then for any of you who are interested in statistics, there is also a free package called R, and R is being used more and more again in industry. So we use Spyder, Jupyter, and within MMU, within mathematics, we also teach our students how to use R. Okay, so this is what Spyder looks like. If you open up Spyder, and if any of you have ever used MATLAB, you'll see it's a very similar setup to MATLAB. So on the left, we have an editor window for writing programs. I'll show you what some programs look like in a moment. In the top window, we have the variable explorer. We can look for help. This is where plots are represented, and we also have files can be shown in this window up here. And console 1A, this console window here, is where we will use Python as a graphing calculator. So you can use Python as a graphing calculator in this window. And again, I will give you some examples of what these look like. Okay, as I say, this setup is very similar to MATLAB. I didn't say this at the beginning, but I should have said that, you know, amongst Python, Maple, MATLAB, and Mathematica, Python is the only software which is freely available. Unfortunately, the other packages cost you money. Okay, so how can we use Python as a calculator? So we can use our console window. So here you see this, you have this prompt in one. Now, for any of you who've used Mathematica, you'll see that this is looks very similar to Mathematica. So we have in one, and we type our commands after this input prompt. Now, in Python, we can insert comments using a hash symbol. So Python will ignore anything after the hash. So in this case, I've just written, this is a comment. Okay, and this is one of the most useful characters in any programming languages, any language. And I'll explain a bit more about that as we go through this talk. You can see into here, I've given a simple example of how you add and subtract numbers. And this is the kind of calculation you can do on a calculator. So later on, I'm going to show you the kind of workshops I run. And the first session, I show students and teachers how to use Python as a graphing calculator, because even if you've never programmed before, most people have used a calculator. So you can add and subtract. To multiply numbers in Python, we use the asterisk, and to divide, we use /. Okay, so this gives us 2 times 3 divided by 6, and this gives us a floating point answer. So the floating point answer is 1.0. And I might, if I've got time, I'll say more about floating point arithmetic later on. We can also take powers, so we can do exponentiation with Python. So 5 asterisk asterisk 30 is the same as 5 to the power 30. And you can just about get away with doing this kind of calculation on your calculator. Okay, now, in order to use functions or extra buttons, if you think about it, on your calculator, we have to import a library called math. So there's a math library with functions like sine and cosine and exponential and factorial. And there are a lot more functions which have been written by people all over the world. So there is a function called factorial. So we can use Python to work out 52 factorial. So to work out 52 factorial, we use the function factorial, and you can see we put 52 in the brackets. And you can see that 52 factorial gives you this number. Okay. For any of you who like playing cards, this is the number of permutations you can have for one pack of cards. Okay. And I'm sure you can see this calculation you would not be able to do on a graphing calculator. Now, as well as performing calculation in that form, we can also perform symbolic computation with Python. And this symbolic Python is very powerful. A lot of computer scientists do not realize that you can use Python for mathematics. So a lot of computer scientists never use symbolic Python, but obviously mathematicians do. So here are some simple examples. So from the symbolic Python library, import star just means we're going to import all of the functions. Yeah, so we're going to import all of the functions from SymPy in order to perform algebraic manipulation or calculus, etc. We declare x and y to be symbolic. So x and y equal symbols xy. And then we can use these functions. So in Python, there is a function called factor. And obviously, this is used to factorize polynomials. So factor x cubed minus y cubed will give us x minus y multiplied by x squared plus xy plus y squared. And you can see that's very powerful. I'm just giving you a few simple examples here. From within the SymPy library, we've also got the function diff, so we can differentiate. So we differentiate the polynomial 4x cubed minus 3x to the 4 with respect to x. I should say this diff command, you can also do partial differentiation as well. So we can differentiate with respect to x and y if you wanted to. As well as differentiation, and another function important in A-level mathematics is obviously integrate. So we can perform indefinite or definite integration with Python. So the function in Python, not unsurprisingly, is called integrate. So this is integrating this polynomial, and x goes from -2 to 2. So this part of this function gives us the limits on our integral. Okay, another library which is very popular in Python is Numerical Python, and so it's abbreviated to NumPy. So NumPy is yet another library, and this is where we perform Numerical Python. We can set up a list. So A is going to be a list of numbers, and range 5 means we're going to go up to 5. Now, I wanted to show you how Python differs from other programming languages. Python uses what we call zero-based indexing. So this list of numbers, list range 5, for example, in MATLAB, this would give us the numbers 1, 2, 3, 4, and 5. Yeah. But because Python uses zero-based indexing, this gives us a list of numbers beginning with 0. And we go up to, but we do not include 5. So the list of numbers range 5 gives us 0, 1, 2, 3, and 4. So this is zero-based indexing. To access the elements in a list, we do A and then square bracket 0. This gives us the first element in the list. A1 will give us the second element in the list. A2 will give us the third element in the list. A3 would give us the fourth element in the list. And finally, A4 would give us the fifth element in the list. So whenever you're using Python, it's important to get your heads around this zero-based indexing. So we use lists a lot in Python, and we use something called an array. Okay, so this is an array, and for those of you who are mathematicians, you'll see, well, this just looks exactly like a matrix. Okay, but it's important to distinguish between arrays and matrices. Okay, because there is a definite matrix algebra. But with these arrays are much more powerful than matrices. And if any of you are interested in machine learning and deep learning and artificial intelligence, we use these arrays a lot, and we use something called tensors. So we use tensor algebra rather than matrix algebra. And the reason for that is because tensors are far more powerful than matrices. Okay, but we can also, within Python, we can also do matrix algebra as well. But the reason I want to show you these arrays is because one of the big applications of Python at the moment is in deep learning and machine learning and artificial intelligence. So most companies around the world are now using Python for machine learning and deep learning, and they're using something called TensorFlow. Okay, TensorFlow uses these tensors, and this is very powerful computation with machine learning and deep learning. Okay, how do we get simple plots in Python? Well, we need the numerical Python to set up the domain. So in this case, X. Here we are using NP as an alias for NumPy. And within NumPy, within the NumPy library, there is a function called linspace. And linspace will give us, in this case, it will give us the X values from 1 to 5, and it will split it into 50 equal parts. Okay, so this is defining our domain for our function. And then to plot, we import matplotlib.pyplot. So this, again, is using libraries, and we import a PLT. So we're going to import this library and just call it PLT. So again, this is the alias for matplotlib.pyplot. pyplot. And you'll see in this case, we are defining y as 3 times x minus 1 times 5 minus x over 32. Okay, so here we have our inverted parabola. And to plot this, it's simply PLT. So we call this library, and then within this library, there is a function called plot. Okay, so this is the function plot. And we simply plot x against y. So again, you can see this is very similar, again, to MATLAB. So we're just plotting the x values against the y values, and we've got 50 points in between. So we just use straight line segments, and you see we get this nice smooth curve. And obviously, the more points you put in your Lynch space, the smoother the curve you obtain. But obviously, you take up more memory doing that as well. And the plot, you will see, appears in the plot window within Spyder. Okay, so I've been talking a lot about these functions. Well, one of the strengths of having a programming language is that you can define your own functions. And this is what makes programmers so sought after in the job market. So I'm going to give you a very, very simple example of a function. So in this window here, remember this was the window where we can write our functions. We are going to define a function. It's a little bit like adding a button to our calculator. And we're going to call our new function SQR, square. And the argument we're going to use is x. So our function is square as a function of x. And whenever we define a function in Python, we have to end the line with a colon. Okay, when you hit return after typing this, Python automatically indents for you. And indentation in Python is vitally important. So you have to let Python do the indentation for you. So here we define the function. We then run the script. Oh, sorry, we have to save the function. So now we've got this files. So we save the function as SQR, and all Python files end in .py. So we've saved the file. We run the script using this play button, and you can see here we've run the script. And once we've run the script, then we can call the function. So you'll see then in the command window, we type SQR is our new function, and we put x is minus 6, and you can see we do get out 36. Well, you can see once you've done this, it's very easy then to give this as an example to students, and they can define their own functions. So you can define your own functions, a bit like creating your own buttons on your calculators. So that's our first type of command in Python, defining functions. Next, I'm going to show you loops. So loops are also important in programming. So here we are going to define our second function. We're going to call it Fibonacci. And again, you can see here we save the file as Fibonacci.py. Here is our program. So in Python, we can list the commands like this. So A, comma B, we're going to define A to be 0 and B to be 1. And you'll see we can do all of this on one line. We're then going to print A and print B, which we do here, print A, print B, and then we print A plus B. Yeah, print A plus B gives us this value. So those are the first 3 terms of the Fibonacci sequence. Then we need a loop. So for the remaining numbers in the sequence, we have for I in the range n minus 3, because we've already printed out the first 3 values. We're going to say A goes to B, B goes to A plus B, and then we print A plus B. So on every loop, we print this A plus B. So you can see that's how we get 0 plus 1 gives us 1, 1 plus 1 gives us 2, 2 plus 3 gives us 5, 3 plus 5 gives us 8, etc. And this gives us the Fibonacci sequence. You'll also notice at the end of this for command here, again, we've got a colon. Okay, so we need a colon when we define a function, and we need a colon for our for loop. Okay, so that is a very simple example of a loop, of a for statement. So we now know how to define functions. We know how to construct for loops. And then finally, we need this if, then, else. And believe it or not, with these 3 constructs, you can write any program. Okay, so how does the if, then, else work? Again, we define a function. We've called this one test integer, and we leave this argument open. So we're going to put the arguments, we're going to ask for the arguments and type it into our command window. So test int is going to be an integer, and we want the user to input something. And we give them the command, enter the integer you wish to test. So in the command window, after you've run the file, you hit return at the end of this test integer, and you get this output, enter the integer you wish to test. So then you will type in a number. You can type in 0 or 100 or 1,000,000 or -1,000,000, any number, any integer you like, and you'll see that you get an output. And depending on what you've typed in, so if your test integer is negative, it will type out the integer is negative. If your test integer was positive, it will print out the test integer was positive. Or if your test integer was 0, so this is your else. If it's not positive and it's not negative, then the only possibility is it was 0. So this is how the if, elif, else construct works. And again, you can see at the end of the if line, you need a colon. At the end of elif, you need a colon. And at the end of else, you need a colon. And Python automatically indents for you. And as I've said, with those 3 constructs, you can write any program. Okay, I'm just going to now show you what a Jupyter Notebook looks like. So from within Anaconda, you can click on the Jupyter Notebook icon, and you'll get a page like this. And then you can open a new Python 3 notebook by clicking on that button there. And this is what it looks like. So here we have a Jupyter Notebook with a program. So here is a program. And to run this program, you'll see there's a button above here. You hit this button here. And again, this is where it looks a lot like Mathematica. For any of you who've used Mathematica, this looks very similar to Mathematica. So this is called a notebook, and they use notebooks in Mathematica. And this is called a cell. And within this cell here, you can see we've got Python code. And within this Python code, you can see we import Numerical Python. We import matplotlib.pyplot as PLT. And then we set these variables here. We give them numerical values. So x0 is 0, y0 is 10, sy is 0, etc. And I'm sure you can see here, this is a problem from A-level mathematics. So this is a projectile. So you can see I've saved this file and called it projectile. So this is what the trajectory looked like when we launch a projectile from the top of a cliff. Okay, so here you have the trajectory of the projectile. So we just use the Suvat equations. And here you can see we just plot the distance in the x direction, distance in the y direction, and we plot a red dot. The x label is range, and the y label is height. And this plt.show just means show the plot. So this is a nice example from A-level mathematics. So that's an example from within the Jupyter Notebook. Within these Jupyter Notebooks, we can also use LaTeX. So we can either use Python code or what we call Markdown. And within Markdown, we can insert LaTeX code, which means we can write mathematical formulae. And on the World Wide Web, these will appear as mathematical formulae. So I'm going to show you my notebooks later, and you can see we can just type in headings. So here we've got heading 3, we're looking at equations and inequalities. We can solve these these non-linear simultaneous equations. Well, one is non-linear, the other one is linear. So this is typical of a kind of problem you get at A-level. And here we're also solving this inequality. And again, we can use Python to get results for these problems. And as I say, later on, I will show you my Jupyter Notebooks, which I've called Python for A-level mathematics and beyond. And you'll see my examples cover the whole of the A-level syllabus. Okay, so as well as downloading Anaconda onto your machine, you can actually use something called Google Colab. And for Google Colab, you do not need to download any software on your machine. All of this is done on the cloud. Okay, so you require a Google account. So if you go to this website here, you can register with Google Colab. You just need a Google account, and you can program in Python for free, and you can also do your computation through the cloud, which means you don't need any software on your own computer. So cloud computing, you don't need any configuration at all. You'll see that this Colab is short for collaboratory, and this allows you to write and execute Python code through the cloud. You also have free access to central processing units, graphical processing units, and even tensor processing units. And believe me, Google Colab is used a lot in industry. And the reason it's used a lot in industry is because you can easily share your files with co-workers through something called GitHub. Okay, so you can write your programs in Google Colab, and then you can save your files through GitHub, and then you can have a number of people working in the same company. All of them can have access to GitHub. So you can have a lot of people working on one program, which is used a lot in industry. So whether you're a student, a data scientist, or an artificial intelligence researcher, Colab can make your work easier. And as I've said, this is being used more and more in industry. So you can watch an introduction to Colab, you can watch a video on this, or you can just go to this website and you can access the video there. So I think this is a fantastic resource for teachers. Yeah, you don't need any software on your computer. You can do all of your computing through the cloud, and then you can save your files to a GitHub repository. So you don't even need to use memory on your computers. And this allows teachers to share and use files. And you can imagine teachers in a school sharing their files through GitHub. And then, if this goes national, then you can have teachers contributing nationally through GitHub. Okay, so this is just an itinerary of the workshops that I run. So you'll see for the first hour, I introduce delegates to Python and I show them how to use that as a powerful graphing calculator. And today I've just given you a little snapshot of what that looks like. Then there's a 15-minute coffee break. Then at 11:15 till 12, I show delegates how to use Symbolic Python, so how you can differentiate, integrate, etc. Then there's a break for lunch. And in the afternoon, I introduce Numerical Python and how you can plot using Numerical Python and Matplotlib. And then after the final coffee break, we then look at simple programming and how to use Jupyter Notebooks, how to use Google Colab, and then I explain a bit about beyond A-level mathematics. Okay, if you're interested in my research, I am on ResearchGate. So again, I've given the URL, but if you simply type in ResearchGate into Google, ResearchGate and Stephen Lynch and Manchester, then you can easily find me. So you can download all of my journal papers through ResearchGate. And you can see that because of my books, there have been 62,000 reads of my papers. And a lot of researchers around the world are now signing up to ResearchGate. And this means that anybody in the world can access our research free of charge. You don't have to pay journal, you don't have to pay the journal subscriptions, etc. Okay, these are just some of my publications to do with Python and programming. So in 2020, the Maths, Stats and Operational Research Society, and there's a journal called MSOR Connections. So in 2020, there was a special issue on programming in mathematics. And you'll see that I wrote a paper, it was entitled Programming in the Maths Curriculum at Manchester Metropolitan University. So that was only published a few months ago. In 2016, I did some work with Abel Naya Mapfeen, who's a teaching fellow from University College London. And we wrote a paper entitled Systematic Integration of MATLAB into Undergraduate Maths Teaching. And this was preliminary lessons from MMU and from UCL. And then finally, in 2015, the European Society of Engineers had an annual report, and they reprinted a report which was written by myself and Jay Wilbur from MathWorks. And this was a story about Manchester Metropolitan University students vote math best overall course following the adoption of MATLAB. So that was a MathWorks user story. And as I say, if you're interested in these publications, you can download all of those through ResearchGate, and you can read those in your own time. So I've written a book, Dynamical Systems with Applications Using Python. There is a GitHub repository, so all of the Python programs associated with this book can be downloaded through GitHub. Okay, so you can download all of these Python programs through GitHub, or similarly, you can go on the World Wide Web, just go to this web address here, and you can see all of the Python programs. But what's beneficial about this is you can also see the output. Yeah, so you can see the output from the programs. We'll say a bit more about that later if we have time. So I'd like to thank you. That's 45 minutes. So I want to leave some time for questions. The picture at the beginning was what we call a Newton fractal, and it's generated using the formula Fz equals z cubed minus 1. This is program 15D in my book, and you'll see that we use the Newton-Raphson method, which you use at A level. So this is the formula from the Newton-Raphson method, and this gives us this very pretty Newton fractal. Okay, Rachel, I better stop there. I could go on forever, but I think we should give people a chance to...
Thank you, Stephen. Thanks for that talk. It's clear to see that there's lots of potential for using Python at A-level maths. And we've got quite a few questions coming in, so we'll do our best to get through them. So the first one's from Mataba, who says, why is Python on top rank compared to MATLAB, particularly these days?
Okay, I think the simple answer to that one is MATLAB can be quite an expensive package for industry. Yeah, and as you saw, from the earlier slides, only 2% of people in the world use MATLAB in industry. Yeah, so recently Python is by far the dominant programming language. But the main answer is Python is completely free, and it's what's called open source. So anybody in the world, can create these libraries and packages, and there's kind of a real community feel among Python users. So that's why it's such a popular language. And as I said, it's a general purpose programming language. So it's used by a diverse range of industries in the real world.
Okay, that's great. Next question is from Ibrahim. Would you recommend Jupyter or Spyder for foundational year university students?
Yeah, they're both equally as good as each other. The major benefit with Jupyter is you can put your notebooks on the World Wide Web and make it available to anybody. But with Spyder, obviously you can't really share. You can put them in GitHub, but it's much easier with Jupyter Notebooks to post them on the World Wide Web, and then people can have access. I think I'm still sharing my screen. Am I, Rachel?
Yes, you are.
Yes. Let me just show you what I mean by that. So I'll show you my web page. I've got it up and running. Okay, so this is the Jupyter Notebook for Python for A-level mathematics and beyond. Okay, so you can see that this is from Maths, Education and Innovation, and you can see that these are the schemes of work. There are 42 schemes of work. And if you scroll down here, you can see that I go through all of the schemes, and there are examples of MATLAB commands and MATLAB programs to show that Python covers the whole syllabus. And even within the web pages, we can
actually see what you're referring to. We can still see your thank you slide.
Oh, right. Hold on. Let me.
Sorry to interrupt you there.
No, that's good. Let me try and change. How do I change? So screen sharing. If I stop sharing, and then I'll try and share again, but now I'll share with my desktop. Okay,
yes.
So you can see that?
Yes.
Okay, so yeah, so sorry. So this is these are the Python web pages for Python for A-level maths and beyond, and I'll show you how to access that in a second. As you can see, that there are schemes of work here, 42 schemes of work, and as you scroll down, I've given lots and lots of Python examples, for these schemes of work, and there's even an animation here. So this is what I meant with, you can show the animation once, or you can reflect. So you can click on this, and you can actually get it to reflect. So this is all live on the World Wide Web. Or you can even pick this up yourself and just, you know, have a quick go at the animation. It's very flexible. So you know, it covers the whole of the A-level syllabus. How do you access this? If you go to my web page, let's just get my web page. Sorry about this. To try and do this quickly. If you go to my web page, so Stephen Lynch, Manchester Metropolitan University, here, and if you go to schools liaison, so I run a schools liaison as well, go into schools and give talks. You'll see that there's a link here, teaching coding in schools, and there's a link, Python for A-level maths and beyond. And that takes you to these web pages. So that's how you access those web pages.
Okay, thank you. The next question is from an anonymous person. And they're asking, if you want to learn Python from scratch, what would you recommend?
The best way to learn Python is come to one of my workshops. I run these workshops in one day. What you learn in that one day, I'd say, is equivalent to 1 month trying to learn it on your own through books, honestly. And I know this for a fact because, you know, I've had to learn so many different languages, and I've had to teach so many different languages to so many different people. And these workshops are invaluable. You know, honestly, what you can learn in one day can save you many, many hours of reading through books.
Okay, next questions are from Danny. She's got 2 questions. The first one is, would you suggest that pre-teaching some Python, for example, in Key Stage 4, could be beneficial? And then she's asked, she's coded before but never used Mathematica or MATLAB. I think she means MATLAB there. Would you suggest that I familiarise myself with them?
No. The only programming language you will need is Python. Yeah, and to tell you the truth, I'm pretty sure now that I know they use Scratch in many primary schools around the world, and Python is definitely being taught in secondary schools around the world. We are finding a larger percentage of our students are coming to us, you know, from school. I'd say about 50% of them have now met Python at school. So just stick with Python.
Okay, that's useful to know. And this next question is from an anonymous attendee as well. What do you think it would take for, say, the exam board's OCR or AQA to include Python in their A-level maths or further maths courses?
Yeah, we can't just do this overnight. It's going to have to be a long haul, I'm afraid, because we would have to teach all of the teachers in the country to program in Python. And then before we teach the school pupils. I don't know if any of you have used the MEI, but Tom Button is a technology expert with the MEI, and they already have a unit in the further maths. It's called further maths, further pure maths with technology. So they already do this, but I think there are currently only about 5 schools in the whole country who offer this to their students. So we will not be able to, you know, start this next year or the year after. My idea for this is to have Python clubs in schools where students can study Python alongside the A-level maths to help them understand their A-level maths more.
Yeah, it seems like there's lots of potential there, doesn't it, to help the students. Ibrahim's asking, looking ahead, do you think Python will replace MATLAB for university mathematics teaching?
I'm not really sure about that, because MATLAB is fantastic. You know, we still use MATLAB now, so we haven't replaced MATLAB with Python. We teach both. And if you look at the report by Philip Bond, he does say that he recommends that you know, students learn 1 or more languages. So I think it's fine if students learn Python with MATLAB or Python with Maple or Python with Mathematica. One of the major hurdles we've had in the past, so I've tried to do this, say 10 years ago, I ran workshops, you know, A-level maths with Maple or A-level maths with Mathematica, and I even negotiated with MathWorks and MapleSoft and Wolfram, you know, to get cheaper licenses for the school. So I negotiated for the schools could get a license, say, for Mathematica for £50. But what we found is that the schools were coming back to us and saying, we can't afford £50. So I hit a bit of a brick wall when I tried to run these workshops with MATLAB, Maple and Mathematica. But of course, now with Python, because there's no charge at all, I don't see any barriers at all to introducing this to school teachers and to school pupils.
Yeah, no, I think schools are very appreciative when things are free. James is asking, in my experience, Python can be a little tricky to set up for novice computer users, especially at home without clear support in place. Does Anaconda overcome this difficulty?
I would say yes. And to tell you the truth, if you do have difficulty with this kind of thing, there are so many videos now available, say through YouTube. So if you go to YouTube, I'm sure lots of people have produced videos on how to set up Anaconda onto your computer. So you just, it's very simple though. You just download Anaconda onto your computer, you open Anaconda, and then you can see there's this launch Spyder or launch Jupyter Notebooks. If you don't like the idea of that, the best place to start is through Google Collaboratory. So in Google search engine, just type in Google Colab, and then you can open up a new Python 3 notebook within Google Colab. So that means you don't need anything on your computer at all, and you can start to write simple Python commands in Google Colab.
Okay, that's good to know, thank you. Aditya asks, I learned to program in Python using IDLE. Is there an advantage other than graphing in using Jupyter Notebooks or Spyder?
Okay, yeah, the problem with Python idle is you cannot perform scientific computation through idle. So you don't have all of these additional libraries like the Symbolic Python and Numerical Python and TensorFlow and things like that. So I also run workshops on Python for scientific computation and TensorFlow for artificial intelligence, but that is a 5-day-long workshop. And I do start that workshop by showing students how to use idle. So that is a very gentle introduction to Python. But you know, for A-level mathematics, it's best just to skip straight to Jupyter, Spyder, or Google Colab, because we need the Numerical Python library and we need the Symbolic Python library, which are not available through idle.
Yeah, I think following on from that question, your explanation and your answer to that, I think this question, which is from another anonymous attendee, follows on nicely. What is the quality control on the routines in the various libraries?
I think the quality control is just the user community. There are so many, hundreds of thousands of people who use Python that if any functions are written, because they are used by so many people, I'm pretty sure, it's kind of like the best quality control you can have in the world. So for example, we've got MATLAB, say, or Wolfram or MapleSoft. They have, say, 1,000 employees or a few thousand employees who are, writing their programs and algorithms, and they check it all works correctly. But for Python, because it's open source, you've got hundreds or if not millions of people who are running this code and checking it for errors. So I would say the quality control is probably better with Python than the other packages.
Okay, I think we might have to make this our last question. But would you be happy to hang around for a few minutes, Stephen, to answer any other questions? Because we've still got quite a few that I don't think we're going to get through.
Yeah.
So this last question is from Danny, and they ask, how different is this as an option to GeoGebra?
Okay, so by teaching students how to program with Python, we give them the tools so that they can, for example, make their own apps. Things like GeoGebra, Desmos, and some of these other things, they're like apps. So they're fantastic. They are fantastic for explaining like animations, and you can differentiate, you can integrate, you can do all the things with Python. But what you can't do is you cannot create your own functions. So Python, again, is far more powerful than Desmos or GeoGebra or these other tools that are used currently at A level. And when we come to employability, if you go into the workplace and you say that you're an expert Desmos user or GeoGebra user, that is not the same as saying that you are a Python programmer. So the main difference is with Desmos and GeoGebra, you can use these apps and these packages, but with Python, you could write your own apps. You could create your own version of GeoGebra or your own version of Desmos, which is what employers are after.
That's great, thank you. It is 5 o'clock now, so I think we will have to stop there. But I'd just like to say a huge thank you to Stephen for a very thought-provoking talk. Thank you so much, Stephen. And thank you to everyone for joining us today.